A machine on a laboratory bench solved a problem that would take the fastest ordinary computer longer than the universe has existed. 200 seconds. That was all it took. And when the people who built it tried to explain how, one of the explanations they reached for was this: the calculation did not happen entirely in our universe. Sit with that. I want to be honest with you right at the start, because I respect you too much to do otherwise. That claim, the one in the title, the one that made you click, is not a proven fact. Nobody has picked up a telephone and heard a voice from another world. Nobody has sent a message across some cosmic gulf and gotten a reply. What we have instead is stranger and, I think, more beautiful. We have a working machine, and we have a mathematics that describes what the machine does. And the plainest reading of that mathematics says something that sounds impossible. It says that when this machine works, it is doing an enormous number of calculations at once, in a way that our single, solid-looking universe does not seem to have room for. So where is the extra room? That is the question. And I've been turning it over for years, and I still cannot put it down. It follows me around. It sits at the edge of ordinary days. I will be washing a dish, and there it is again. You will see why by the end. Here's the gap I want you to notice before we go any further. Most people believe a quantum computer is just a faster computer, a better engine in the same car. That belief is wrong, and the wrongness is the whole story. A quantum computer is not faster in the way a race car is faster than a bicycle. It is doing something a bicycle cannot do at all. It is not running the same race harder. It is on a different track entirely. It is exploiting a feature of reality that most of us were never told about because it does not show up at the scale where we live our lives. At our scale, the world is made of solid things in definite places. A cup is on the table or it is not. Your keys are in your pocket or they are not. Nothing is in two places at once. Nothing is a blend of possibilities. And so we grow up assuming that is simply how everything works all the way down. It is not. And once you see what that feature is, you cannot unsee it. You start to wonder what kind of universe allows a machine like this to exist. You start to look at the solid table in front of you and wonder how solid it really is underneath. Let us find out carefully, one step at a time. Before I tell you what a quantum computer does, I owe you something more basic. How does anyone know anything about the quantum world at all? Because you cannot see it. You cannot hold an electron in your hand. You cannot watch it the way you watch a bird cross the garden. It is far too small. It is smaller than the wavelength of the light your eyes use to see anything at all, which means light itself is too clumsy a tool to catch it. Think about that for a second. To see something, light has to bounce off it and come back to you. But these objects are smaller than the light itself. It would be like trying to feel the shape of a single grain of sand by rolling boulders over it. The tool is bigger than the thing. So where does the confidence come from? It comes from prediction. That is the only currency that counts here. Someone writes down a piece of mathematics. The mathematics says, if you set up your experiment this way, you will get this result this often to this many decimal places. Then you do the experiment, and the number comes back, and it matches. Not roughly, exactly. To more decimal places than almost anything else humans have ever measured. That, and only that, is why we trust any of this. That is what quantum mechanics is. Quantum mechanics is the set of rules that describe how the smallest pieces of reality behave. And it is, by the measurement of prediction against result, the most successful description of nature we have ever written down. When I say successful, I mean something specific. There are predictions in this theory that match experiment to 12 decimal places. 12. Let me make that real for you, because a number like that just slides past if you let it. Imagine measuring the distance from here to the moon roughly 240,000 miles, and being correct to the width of a single human hair. That is the kind of agreement we are talking about. Now imagine doing that not once by luck, but again and again and again, every time you check for a century. That is not a lucky guess. That is not a theory that sort of works. That is a description of nature so precise it feels almost indecent. So when the theory tells us something strange, we are not free to shrug it off. The theory earned our trust the hard way. It paid in decimal places. When something has been that right, that many times, you listen when it says something you do not like. Now here is the trouble. There is a second great theory of the world, and it is just as successful in its own territory. That theory is general relativity, the description of gravity, of how mass bends space and time. General relativity governs the big things: planets, stars, galaxies, the whole shape of space-time, the single fabric that space and time turn out to be woven from, not two separate things, space over here and time over there, but one fabric, and heavy objects sag into it the way a bowling ball sags into a trampoline, and that sagging is what we feel as gravity. General relativity has also been tested again and again. It predicted that light would bend as it passed the sun, and it does by exactly the amount predicted. It predicted that clocks would run slower deep in a gravitational field, and they do by exactly the amount predicted. This is not a curiosity. Your satellite navigation, the little arrow that tells you where you are, would drift by miles within a day if the engineers ignored it. The clocks on those satellites, high up where gravity is weaker, tick faster than the clocks on your wrist, and the system corrects for it constantly, using general relativity every second you drive. It has never once failed. So we have two theories, both flawless in their own domains. And here is the wound at the center of physics. They cannot both be right as they are currently written. Put them in the same room, ask them about the center of a black hole or the first instant of the Big Bang, and they contradict each other. They give nonsense, infinities, answers where the numbers run off to infinity and stay there, which is the mathematics waving a flag that says the description has broken. In every ordinary situation, gravity is so weak on the scale of a single particle that you can simply ignore it, and the two theories never have to meet. Drop an electron, and its gravity is so faint that no instrument we have ever built could measure it. So quantum mechanics runs the small world, general relativity runs the big world, and they politely stay out of each other's way. But at the center of a black hole, you have an enormous amount of mass crushed into a space smaller than an atom. Now, both theories apply at once. Now, gravity is not weak because the mass is huge, and the space is tiny because it is quantum. Both descriptions are shouting at the same moment about the same place. And the two most tested ideas we own start screaming different answers. That is not a small footnote. That is the central unsolved problem. Two descriptions of one reality that will not agree. And every honest attempt to fix it, string theory among them, is exactly that. An attempt, not a settled answer. I will keep saying that because it matters. String theory is a proposal that the smallest things are not points but tiny vibrating strings, and that the different particles we see are just different notes played on those strings, like different notes on a single violin. It also proposes that reality has extra dimensions, more directions than the three we move in, folded up too small to notice, and that these ideas, if true, would let gravity and the quantum world finally sit at the same table without screaming. It is elegant. It is beautiful. It has occupied some of the finest minds alive for decades, and we have never once tested it. We do not yet know how to. The strings, if they exist, are so unimaginably small that no collider we could build on Earth could ever reach them. So when I mention extra dimensions or a hidden layer beneath particles, I am telling you about a proposal, not a discovery. Hold the two apart in your mind, the tested and the proposed. Keep them in separate hands and never let them blur together, because the whole honesty of this story depends on knowing which is which. So how do we know anything about parallel universes, then, if we cannot visit one? We do not in the sense of proof. What we have is a piece of tested mathematics, quantum mechanics, that describes what happens. And when you ask that mathematics what its own symbols mean, the honest answer is that nobody fully agrees. The equations work. Everyone agrees the equations work. There is no argument there. Every physicist in every country, using every version of the theory, gets the same numbers, and those numbers match the world. The argument is about the story. The equations are a set of instructions that always give the right numbers. But the story we tell about what those instructions describe, about what is actually out there behind the numbers, that is where a century of disagreement lives. And a quantum computer, it turns out, is a machine that lives right on top of that disagreement. It is built out of the very thing we cannot agree about, which is why it is the perfect place to begin. Let me give you the simplest picture I can, and I promise it is enough to carry us all the way. Picture a coin. An ordinary coin. It is either heads or tails. When it is lying on the table, it is one or the other. You can cover it with your hand. You cannot know which it is, but it is already one or the other under there. Your not knowing is just a fact about you, not about the coin. The coin has already decided. That is your everyday world, the world where your intuition works, the world of solid, definite things. A regular computer is built from coins like this. We call each coin a bit. It is a 0 or a 1, heads or tails, off or on, a tiny switch that is either open or closed. Everything your phone does, every photograph you have ever taken, every song, every video you have ever watched, every word of this that reaches you is a pattern of these coins, billions upon billions of them, flipping between two states, faster than thought. That is all it is. Definite, countable, solid. A computer is a vast, disciplined field of coins, each one committed to being exactly one thing. Add them up, arrange them cleverly, and you get everything from a text message to a weather forecast. But underneath, always coins, flat coins, each one either heads or tails, and never both. Now I want you to imagine a different kind of coin, not lying flat, spinning. While that coin is spinning in the air, ask yourself, is it heads or tails? And the honest answer is that the question does not quite apply yet. Here is the part your everyday mind wants to resist, and I want you to resist it. Because feeling the resistance is how you know you have understood. It is not secretly won and hiding it from you. It is not that the answer exists and you simply have not looked. In the quantum world, it is genuinely in a blend of both, not undecided in your knowledge, undecided in reality itself. There is a difference, and it is the whole difference. With the flat coin under your hand, the answer exists and you lack it. With the spinning quantum coin, the answer does not yet exist to be lacked. Physicists call this superposition. The word means what it sounds like. Two possibilities laid over each other, both real, at the same time until the moment you catch the coin and look. A quantum computer is built out of spinning coins. We call each one a qubit, and a qubit, while it spins, is not a 0 or a 1. It is a living combination of both, and it will stay that way until something reaches in and forces it to choose. Here is where your intuition should start to protest, and it is right to. One spinning coin is not so impressive. So what, you might say? A coin in the air. Give it a moment and it will land, and then it is just heads or tails after all. But watch what happens when you have many, because that is where the ground shifts under your feet. Take two ordinary bits. They can be in one of four states, 0, 0, 0, 1, 1, 0, 1, 1. But at any given moment, they are in exactly one of those four. One arrangement. That is the key. One at a time. If you want to consider all four, you have to go through them one after another, like reading 4 lines on a page. Now take 2 qubits, 2 spinning coins. They are in all 4 arrangements at once, blended together, all 4 contributing, all 4 real, not one line at a time. The whole page held open, all at once. Add a 3rd qubit, and you get 8 arrangements at once. A 4th, 16. A 5th, 32. Every single qubit you add doubles the number of arrangements held simultaneously. This is not addition. This is doubling on doubling on doubling, and doubling is a monster. Let me show you how fast this monster grows, because the numbers are the whole point, and I do not want you to just nod along. I want you to feel the floor drop. 10 qubits, and you are holding a bit over 1,000 arrangements at once. 20 qubits over 1,000,000, 30 qubits over 1,000,000,000, 40 qubits over 1,000,000,000,000, 50 qubits, and you have passed 1,000 trillion, a number so large that if you counted one arrangement every second, you would need longer than the age of the universe, and we are only at 50 coins. By the time you have 300 qubits, the number of arrangements held at once is larger than the number of atoms in the observable universe. Let me say that again slowly, because it should stop you. 300 spinning coins. Not 300 billion, not 300 trillion, 300. And the number of possibilities held at once outnumbers every atom in everything we can see, in every direction, all the way out to the furthest edge. Every star, every galaxy, every grain of every dust cloud between them, in one machine, on one bench, in a box you could stand next to and rest your hand upon. Now, sit with that. Where is all of that being stored? A computer with 300 qubits is a small object. You could hold the important part in your hand, the chip itself, smaller than a coin, and yet, if we take the mathematics at its plain word, it is tracking more numbers at once than there are particles in everything we can see, out to the cosmic horizon, the furthest edge from which light has had time to reach us in the entire history of the universe. That is not a metaphor. That is not a way of speaking. That is what the equations say the machine is doing, and those are the same equations that pay in 12 decimal places, the same equations that have never once been caught lying. So either those numbers are being stored somewhere we have not accounted for, or the word storage is the wrong word entirely, and reality is doing something we do not have language for. And this is the exact point where one honest, sober reading of the mathematics whispers something extraordinary. Maybe the calculation has more room than our universe alone provides. Maybe the extra arrangements are not squeezed into this one small machine. Maybe they are spread across a vast landscape of parallel possibilities, all equally real, and the machine is simply the place where they briefly touch the narrow neck of an enormous hidden hourglass. I need to be careful here, because this is the turn. And I want you to feel exactly how firm the ground is and exactly where it goes soft. What is firm? The machine works. You can build it. People have. You can order time on one over the internet right now from a laboratory that will run your calculation and send you the result. The doubling is real. The mathematics that predicts its behavior is the same tested mathematics that pays in decimal places. None of that is in doubt. What is soft, the story about parallel universes, is one interpretation of what that mathematics means. There are others, and I will give them to you fairly, because you deserve to weigh them yourself and not be handed a conclusion. But here is what makes the parallel universe reading so hard to dismiss out of hand. It is not a wild add-on that someone bolted on for excitement or for headlines. It is what you get if you take the equations completely literally and refuse to sweep anything under the rug. It is, in a strange way, the least imaginative reading. It adds nothing. It removes nothing. It simply says every possibility in the mathematics is a real thing somewhere. Nothing is pretend. Nothing is just for show. Nothing is quietly deleted at the end. And if you accept that, a quantum computer stops being a strange, faster machine. It becomes a device that borrows computational power from copies of itself, running the same problem in universes alongside our own, and pools their work into a single answer we get to read. Let me build a completely fresh picture, because I want this idea to arrive from a second direction on its own feet, owing nothing to the first. Forget computers for a moment. Forget qubits. I want to talk about a single particle of light traveling through empty space toward a screen. In front of that screen, we place a barrier with two narrow slits cut into it, two openings, side by side, very close together. The particle of light goes through, and it lands on the screen, and it makes a single dot, one particle. So far, so ordinary. This is exactly what you would expect from a tiny bullet fired at a wall with two gaps in it. Now send another particle, another dot, and another. And you let this run, one lonely particle at a time. Thousands of them, tens of thousands, each one released alone, each one crossing the barrier alone, each one landing as a single dot with the whole apparatus empty behind it. No two particles are ever in the machine together. There is never a crowd. There is only ever one lonely traveler at a time. And you step back and look at the pattern all those dots have made together. You would expect two bright stripes on the screen, one behind each slit. Two piles, where the particles went through one opening or the other, because what else could a particle do but go through one hole or the other? That is what marbles would do. That is what raindrops would do. That is what your intuition screams must happen. That is not what appears. What appears is a pattern of many stripes. Bright, dark, striped across the whole screen, evenly spaced, unmistakable. Not two piles, many bands. That stripe pattern has a name and a meaning that is not in dispute. It is the signature of waves overlapping. When two waves meet, in some places the crests line up and add together and grow tall, and in other places a crest meets a trough and they cancel out to flat nothing. Bright where they add, dark where they cancel. We have known that about waves for centuries. You can see it where two ripples cross on a pond, the little grid of calm and choppy that forms where they overlap. But we did not send waves across a pond. We sent single particles, one at a time, each one utterly alone. So what did each particle overlap with to make a striped pattern of adding and canceling? There was nothing else there. It was alone. There was nothing for it to interfere with except somehow itself. Read that again slowly, because I had to read it perhaps 5 times before it truly landed, and even now it makes the back of my neck prickle. A single particle, sent alone, behaves as if it went through both slits at once and interfered with itself. It explored both paths. It was, while nobody was watching, in superposition, spread across both openings as a blend of possibilities, a wave of maybe. And only when it struck the screen and was, in effect, measured, did it collapse into a single definite dot. Now here is the part that turns the knife, and this is the part almost nobody is told. If you place a detector at the slits, a little watcher to see which one the particle actually goes through, the striped pattern vanishes, gone. The moment you look, the particle picks one slit, like a good solid thing, goes through it and only it, and the two plain bright piles come back. The marble behavior returns. Watching changes the answer. Not because your eyes are magic, not because you disturbed it clumsily, though people used to hope that was the loophole, hoping the detector just bumped the particle off course. That hope has been tested and closed. You can make the detection as gentle as you like. It does not matter. The stripes still vanish. Because the act of extracting definite information, of the universe recording which slit, forces the blend to collapse into one outcome. Knowledge itself is the trigger, not force. Not disturbance, knowledge. So which slit did it go through when nobody watched? The mathematics does not say one slit. It does not say the left or the right and keep it secret. The mathematics carries both paths forward, both real, both contributing, right up until measurement. And now we are standing exactly where the quantum computer stood, arrived at by a completely different road, starting from a beam of light and two cuts in a wall. The same question, what is the status of all those possibilities that the mathematics carries along? One reading says they are just bookkeeping, a clever tool for calculating odds, and only one of them is ever real, and the maths merely tracks our ignorance. Another reading, taken just as seriously by serious people, says all of them are real, each in its own branch of reality, and what we call measurement is simply the moment our particular branch parts company from the others. That second reading has a name people use, and you have heard it, the multiverse. And I want you to notice that we did not go looking for it. We were not hunting for other worlds. We were not trying to be dramatic. It walked out of a barrier with two slits in it, uninvited, the moment we refused to lie about what the mathematics said. Now let me hand you a third picture, and this one is about the machine again, but sharper, closer to the metal. When a quantum computer runs, the qubits are all spinning, all blended, exploring an enormous forest of possible answers at once. But here is the problem the engineers actually face day to day in the real cold rooms where these things live, and it is the most revealing detail in the whole subject. If those qubits touch the outside world even slightly, if a stray bit of heat or a single wayward particle of light or a faint tremor from a truck passing outside brushes against them, the blend collapses. The spinning coins fall flat. The superposition is destroyed instantly. Engineers call this decoherence, and it is the enemy of every quantum machine ever built. It is the thing they fight every single day. It is why these computers must be cooled to a temperature colder than deep space, a hair above absolute zero, colder than the empty space between the stars, where the only warmth is the faint afterglow of the Big Bang itself. It is why they must be shielded from every stray field, isolated from every vibration, hung in silence more perfect than almost anywhere in the natural universe. They are wrapped in layer after layer of shielding, suspended so that no footstep in the building reaches them, sealed away from every whisper of the ordinary world. Because the quantum blend is exquisitely, almost unbearably fragile, the faintest contact with the ordinary world snaps it back into a single definite answer, and the whole computation dies before it finishes. A qubit can hold its blend for a tiny fraction of a second, and the entire race is to finish the calculation before the world notices and slams the blend shut. Sit with what that means, because it is the same thing, wearing a third mask. The very moment the outside world learns anything about the qubits, the many possibilities become one. That is the same collapse from the two slits, where the detector at the opening killed the stripes. That is the same collapse when you catch the spinning coin in your fist. 3 situations, 1 law. The blend survives only in the dark, only in the untouched, only where no information leaks out. And now stand it up next to the computation itself. The machine's whole power comes from holding many possibilities open at once. Its whole fragility comes from those very possibilities collapsing the instant reality peaks. So the engineering challenge and the deep philosophical mystery are not 2 problems. They are 1 problem seen from 2 sides. To make the machine work, you must keep the branches of possibility from touching our ordinary branch until precisely the right instant. You are, in the most literal engineering sense that anyone has ever faced, managing the boundary between the many and the one. That is your job. That is what the cold and the shielding and the silence are for. To hold open a door that the universe is desperate to slam shut just long enough to get your answer through it. And here's the anchoring thought, the one almost nobody points at directly, and I want you to look right at it. When a quantum computer gives you an answer, it does not hand you all those countless possibilities. You do not get the forest. It hands you one answer, 1 dot on the screen, so to speak. So how does it choose the right one out of that astronomical crowd? If it just picked at random from all those possibilities, it would be useless, no better than guessing. The trick, the real art of building these machines, the thing the clever people spend their lives on, is arranging the spinning coins so that the wrong answers cancel each other out, like the dark stripes on the screen where crest met trough, and the right answer adds up, like the bright ones where crest met crest. The machine does not search the forest of possibilities 1 path at a time, checking them off like a librarian going shelf by shelf. That would be no faster than an ordinary computer. It lets all the paths interfere with one another all at once. So the false ones erase themselves and the true one rings out loud and clear. Read that carefully. Interference. The very same word from the 2 slits. The very same phenomenon, the adding and canceling of overlapping waves. A quantum computer is a 2-slit experiment scaled up into a tool, orchestrated, aimed, put to work. It runs on the same borrowing of many realities, tuned so precisely that when they collapse back into one, the one that survives is the answer you were looking for. It is interference harnessed. It is the striped pattern engineered on purpose so the bright band lands exactly on the truth. So now let me draw the 3 pictures together because they have been pointing at the same place the whole time, and I want you to watch them converge. Picture 1, the machine that holds more numbers at once than there are atoms in the observable universe on a bench in a box. Picture 2, the single particle that goes through both slits and interferes with itself and stops the moment you look. Picture 3, the fragile blend that does all the work and collapses the instant the world so much as touches it. 3 roads, 1 destination, each one on its own forces the same question. The mathematics of quantum mechanics carries along a vast crowd of possibilities, all treated as fully real right up to the moment of measurement. And in 100 years, across countless experiments, in laboratories on every continent, nobody has ever caught that mathematics being wrong. So what, then, is the status of that crowd? What are all those possibilities while they are still possibilities? Are they real, or are they convenient fiction the equations use and then throw away? There are, honestly, a few ways to answer, and I will lay them side by side so you can weigh them yourself. One says the crowd is real only as a calculation, a way of tracking odds, and when you measure, the universe simply picks one and the rest were never really there at all. That is clean, and it lets you sleep at night. It is comfortable. It fits the world of the flat coin. But it leaves you unable to say what causes the picking, or why measurement should have such a magical, singular role in a universe that otherwise runs by steady rules with no special moments in it. It puts a special line in reality between the watcher and the watched, and no one can say exactly where that line falls or why. How big does something have to be before it stops blending and starts choosing? Nobody in that camp can tell you. The line is drawn, but nobody can find it. Another answer says the crowd is entirely real, every last member of it, and measurement is not a collapse at all, but a branching. In that reading, when the particle hits the screen, reality does not choose. Reality splits. Every outcome happens, each in its own world, and you go with the outcome you happen to experience, because there is now a version of you in each branch, each equally convinced they saw the one real result. No special line, no magical picking, just endless, quiet branching, all the time, everywhere. This is the multiverse reading, and I have to flag it as clearly as I know how. It is contested, it is not proven. It cannot, so far, be tested against its rivals, because all the readings predict exactly the same experimental numbers. They differ only in the story they tell behind the numbers. But it is not fringe, and it is not lazy. It is what you get when you take the most successful theory in the history of science absolutely literally and flinch at nothing. And here is why the quantum computer sharpens the question to a fine, unavoidable point. In the everyday two-slit experiment, one particle exploring two paths, you can wave the puzzle away by saying it is just a small, strange effect at the ragged edge of things, a curiosity, nothing to lose sleep over. Two paths. Who cares about two? But a quantum computer running a real calculation is exploiting an astronomically large crowd of possibilities to do genuine, useful, valuable work, not two paths, numbers beyond the count of atoms. If those possibilities are mere bookkeeping, empty labels in an equation, then a small object on a bench is performing bookkeeping over more numbers than the observable universe contains particles, and doing it in a couple of 100 seconds, and handing you a correct answer at the end. Where is that computation physically taking place? Point to it. You cannot point to it inside the box, because the box is too small to hold that many numbers as ordinary information. There are not enough atoms in the box. There are not enough atoms in the building. There are not enough atoms in the galaxy. The honest, uncomfortable, wonderful truth is that this is a live and open question. And one serious answer held by serious people is that the extra room is real, that the calculation is genuinely distributed across a landscape of parallel realities, and the machine is the narrow bridge across which their combined effort flows into a single answer we can read. That is what people mean when they say a quantum computer may have touched a parallel universe. Not a phone call, not a voice, not a message. A calculation that seems to need more universe than we have, finding that room somewhere we cannot see and giving it back to us as one clean result on a screen. Notice what all three pictures share at the deepest level, beneath all the detail. In each one, reality at the smallest scale does not have definite properties until it is measured. That is the strangest fact I know. And I want to be clear that it is not speculation. It is not the contested part. It is the tested core of quantum mechanics, confirmed to those 12 decimal places, the thing everyone agrees on regardless of which story they prefer. Before measurement, a blend. After measurement, one outcome. The blend is not our ignorance. The blend is the way things are until the world reaches in. The whole century-long debate about parallel universes is really a debate about one narrow thing. What happens in the gap between the blend and the outcome? Does the world choose, quietly, by some rule we have never found and cannot locate? Or does it split, so that every outcome is taken and nothing is ever thrown away. And a quantum computer is the first machine we have ever built that does real, valuable, world-changing work inside that very gap. It does not live in the world of the flat coin. It lives in the space between the many and the one, and it earns its keep there. That is what makes it feel like a bridge, because in a way that we can measure and cannot yet fully explain, it is one. It is a thing we built that works inside the mystery. So, let us bring it home. We started with an impossible-sounding claim. A machine that solved in 200 seconds a problem that would outlast the universe on ordinary hardware, and an explanation offered soberly that reached for other worlds. And instead of taking that claim on trust, instead of letting a headline do our thinking, we built the ground under it, one plank at a time, so that you could check each step yourself and lean your weight on it as you went. We asked how anyone knows anything about the invisible smallest scale, and the answer was prediction, mathematics that pays in decimal places, the most tested description of nature we have ever produced. We met the ordinary coin, the bit, heads or tails, solid and definite, the humble stuff of every computer you have ever owned or ever will. Then the spinning coin, the qubit, a genuine blend of both superposition, not ignorance, but real undecidedness, and we watched that blend double and double and double until a small machine held more arrangements than the whole cosmos holds atoms. We stepped away from computers entirely and stood in front of a barrier with two slits, and we watched a single lonely particle behave as if it explored both openings at once and interfered with itself, making stripes it had no partner to make. And we watched that magic vanish the instant we dared to look and ask which way it went. We came back to the machine one last time and found its greatest strength and its greatest weakness are the same thing: the fragile crowd of possibilities that does all the work and collapses at the faintest touch of the ordinary world, which is why we bury these machines in cold and silence, deeper than deep space, colder than the gulf between the stars. 3 pictures, 3 roads, 3 completely different starting points, and every single one of them delivering us to the same doorstep. The mathematics carries a vast crowd of real-seeming possibilities up to the moment of measurement, and nobody, after 100 years, knows for certain what that crowd is: bookkeeping or worlds. And the quantum computer takes that ancient abstract question, argued in armchairs and lecture halls over coffee that went cold long ago, and makes it concrete and humming, because it puts that crowd to work and hands us a single answer and leaves us standing there wondering where on earth or off it all that effort actually happened. Now let me be as plain as I can about what is still open, because that honesty is not a weakness of the story, it is the best part of it. We do not know whether the multiverse is real. We do not know whether measurement is a collapse or a branching. We cannot yet design an experiment that would settle it, because every reading predicts the same numbers, and a theory you cannot test against its rivals is, for now, a story we choose rather than a fact we prove. That is a genuine frontier, and it is fine that it is unresolved. It is more than fine. It is thrilling. We are living in the exact moment where a philosophical puzzle, argued for a century over coffee and chalkboards, has become an engineering reality humming quietly in cold laboratories around the world, and the open questions do not stop there. We do not know what is inside a black hole, past the event horizon, that point of no return, beyond which even light cannot climb back out, at the singularity, where our 2 great theories both throw up their hands and hand us infinities instead of answers. We do not know what happened before the Big Bang, if before is even a word that applies when time itself may begin there. We do not know how to make general relativity and quantum mechanics finally agree, and string theory, with its extra dimensions folded too small to see, remains a beautiful proposal we have not yet been able to test. We do not know what the dark matter is that holds galaxies together, the unseen weight that keeps the stars from flying apart. We do not know what the dark energy is that is pushing the universe apart faster and faster, stretching the fabric of space wider every day. We look at the cosmic microwave background, the oldest light there is, and it is astonishingly smooth in every direction. And cosmic inflation is our best guess for why, and even that is a proposal still being tested. We turn our newest telescopes on the early universe and find galaxies that grew up faster and richer than our models expected, and every one of those surprises is an unfinished sentence. All of that is unfinished. And a universe with this much left unfinished is a universe worth paying attention to. It is a universe that still has rooms we have not entered. Here is the thought I want to leave in your hands, and then I will let you go. You woke up today in a world where machines exist that appear to need more universe than we can point to, and they work anyway, right now, today, whatever the final answer turns out to be. And that plain fact remains standing no matter which story wins in the end. Reality, at its root, is far stranger and far more generous than the solid world of your kitchen table ever let on. The spinning coin is more honest than the flat one. The particle that takes both paths is telling us something true about how things really are underneath the calm surface of the everyday. And the machine on the bench is quietly insisting that the door between the possible and the actual is not closed, and perhaps never fully was. You do not need to believe in parallel universes to feel the wonder of that. You only need to notice that the smallest pieces of you, and of everything you love, and of the chair you are sitting in, live in that blended, undecided, endlessly rich state until the world reaches out and asks them to choose. We are not spectators to this strangeness. We are made of the very stuff that these machines exploit. And that, to me, is the most beautiful sentence in all of physics. Thank you for spending this time with me and for letting your mind stretch around something this large without needing it tied up in a neat and tidy bow. If you would like to keep wondering alongside me, consider subscribing, and we will keep walking to the edge of the known together, one careful step at a time.